Welcome to the Physics Lab. Let's just dive straight into today's explainer, because we're focusing on something absolutely crucial for our practical work. I'm talking about wiring circuits safely, without blowing a fuse, or worse, totally frying our expensive equipment. Now, if you've ever stood at your lab bench and felt kind of intimidated by the absolute tangle of wires, batteries, and meters in front of you, don't worry, we've all been there. By the end of this session, you're going to understand exactly what's going on inside our measurement tools and why those internal properties actually dictate exactly how we have to connect them. So here's our quick agenda for today. First, a welcome to the Physics Lab. Second, we'll go through a step-by-step ammeter setup. Third, we're going to look at the real danger of parallel wiring. And finally, we'll do a quick voltmeter comparison.
All right, part one. Welcome to the Physics Lab.
Okay, so looking around at the tools on your benches, you're mostly going to be dealing with ammeters and voltmeters today. And the thing you've got to remember is they aren't just like passive observers standing on the sidelines. They literally become physical parts of your circuit. And because they're part of the circuit, their internal properties dictate exactly how we use them. To really get this, we have to visualize one key concept, and that is resistance. Resistance is just the opposition to current flow in an electrical circuit. I always like to think about this using a water pipe analogy. Imagine the flow of electricity is just water running through a pipe. If a component has very low resistance, it's like this massive, wide-open pipe letting a ton of water rush right through with basically zero pushback. On the flip side, high resistance is like a super narrow, highly restricted pipe that barely lets a trickle through. Keep that wide-open versus restricted pipe analogy in your head because it's going to make our first tool make total sense. Moving right along to part two, step-by-step ammeter setup. Let's see how this actually looks when you're working. We need to know exactly how to wire an ammeter to measure the current flowing through a specific component, like, say, a simple light bulb. Let's walk through this step by step. Step 1, identify your circuit component, so grab your light bulb. Step 2, you actually have to physically break the circuit path open, unplug a wire. And step 3, insert the ammeter right into that exact same path. So why do we do it this way? Well, the fundamental rule here is that current is exactly the same at every single point in a series path. By physically shoving the meter into that path, the exact same current that flows through your light bulb is forced to flow straight through the ammeter.
And that brings us to a massive golden rule for this lab. Quote, an ammeter is always connected in series with the circuit element whose current is to be measured. Write that down. Burn it into your brain. An ammeter is never connected in parallel. It has to become a physical piece of that single, unbroken series path if you want to measure the current accurately.
But wait. If we're forcing literally all of our circuit's current to travel completely through this little box, won't that mess up the circuit? Actually, no. Ammeters have very low resistance, like almost zero. Remember our water analogy? The ammeter is essentially that massive, wide-open water pipe. Because it has almost zero resistance, it doesn't push back on the current flow at all. It allows nearly the exact same current to just flow right through it, meaning your overall circuit current remains totally unchanged. It just observes the flow without slowing it down.
Let's actually trace this out visually. Take a look at the left side. This is the correct series connection. See how the current leaves the battery, flows straight through the ammeter, continues through the bulb, and then returns to the battery in one single continuous loop? Perfect. But now look at the right side. This is the wrong connection. Here, the ammeter creates a separate loop, a little shortcut branching right around the battery or the bulb. And since we know the ammeter acts like a wide-open pipe, what do you think the current is going to do when it sees this super easy shortcut?
And that perfectly tees up part three, the danger of parallel wiring.
Connecting an ammeter in parallel is hands down the most common and honestly the most hazardous mistake I see students make on the bench. It's not just wrong on paper, it's physically dangerous. Let's break down the cascading dangers of that wrong connection we just looked at. If you hook up an ammeter in parallel because of its incredibly low resistance, it creates a super easy path for the current. And electricity is lazy, right? It always takes the path of least resistance. So suddenly, a massive, huge current flows rapidly straight through the ammeter. This sudden surge is going to damage the ammeter, it'll instantly blow the fuse, and it causes dangerous short-circuiting. To put that into perspective, this mimics serious household risks. Think about when a wire frays in your kitchen toaster and accidentally creates an unintended, low-resistance shortcut. It causes a huge current spike that trips your whole house's circuit breakers just to stop a fire. So, wiring an ammeter in parallel, you're basically forcing a short circuit right there on your lab bench. Don't do it.
All right, finally, part four, the voltmeter comparison.
Now that we've totally mastered the ammeter, let's talk about its partner on the bench. The voltmeter has a completely different job.
which means it follows completely opposite connection rules. A voltmeter is connected in parallel because its whole job is to measure the potential difference between 2 points. It's essentially comparing the energy level right before a component to the energy level right after it. But to do this safely, without suddenly stealing all the current away from the light bulb it's measuring, it relies on its internal properties. So while the ammeter was that wide-open pipe, the voltmeter intentionally has very high resistance. It acts like a highly restricted pipe, ensuring it draws just a tiny trickle of current away from the main circuit while taking its reading.
Take a look at this comparison table. This is basically your lab cheat sheet. For the ammeter, the connection is series, and the internal resistance is very low. For the voltmeter, the connection is parallel, and the internal resistance is very high. Seriously, understanding this relationship, what a tool does, how it connects, and its internal resistance will honestly prevent like 99% of wiring errors you'll ever make.
So before we wrap up today's explainer, I really want you to lock these golden rules into your memory. Ammeter means series, which means low resistance. Voltmeter means parallel, which means high resistance. Whenever you're staring down a messy tangle of wires on your lab bench, just recite these rules to yourself. It guarantees you'll know exactly where the current is going, and it'll keep you and our very expensive equipment safe and sound.
So I'm going to leave you with this question to chew on as we finish up today. If your appliance needs a high-resistance path to accurately measure potential difference without completely disrupting the circuit, which tool are you reaching for on your bench? Think carefully about how we've mapped out the flow of current today, and use that to guide your hands in your next experiment. Thanks so much for joining me for this explainer. Stay safe and happy wiring.